Hello everyone, in this video I'm going to share with you guys how to simulate your own stochastic SIR model using MATLAB. I am not going to explain the whole thing about SIR model in this video because in this video I'm just going to my aim is just to show to you to share with you how to write the code for the stochastic SIR model. Okay, so if you want to really understand about the SIR model, I really recommend you to study about it first by watching other YouTube videos, and after you get the idea of the SIR model, then you can come back to this video. Okay, so SIR model is one of the common model that can be used to simulate the spread or to model the spread of a disease. For example, the COVID-19 virus. Okay, so if you're familiar with SIR model, there are actually equations for the model. But if you want to create a stochastic SIR model, we won't actually be using that equations. Now we are going to build our model based on this Markov chain. If this is your first time hearing the terms Markov chain, well, don't worry, because Markov chain isn't that hard to be understood. Let me just explain, and I'm sure that you will get the idea of Markov chain immediately. What's on the screen? This is the Markov chain that I was talking about. Now, as you can see, we have three nodes, the SIR nodes, and this is based on our models, which is the SIR. Now, what this Markov chain tells us is that a susceptibles can be infected with the probabilities of P, I, and F, or the susceptibles will stay susceptibles with the probability of 1 minus P, I, and F, and this is the axiom of probability. And the Markov chain tells us that and infected individuals can be removed with the probability of PREM, okay, or the infected individuals will stay infected with the probability of 1 minus PREM. Now, what about remove? Okay, as you can see, for remove will stay remove, okay, because this is one of the assumption that we've made. Remove is either the infected person that has died, or the infected person that has recovered with 100% immunity, which means remove cannot be infected again. So that's why you don't see any other arrows pointing outwards from remove. Let's see how are we going to write the code for our stochastic SIR model. Okay, so the first thing that we will do is creating a time vector. The time vector is of course the x-axis of our model. So we just create an equal vector from 1 to 100. So the next thing that we are going to create is the vector for the SI and R. And to create the vector, we just create for example, for S, we are going to create the zeros vector with one row. This is the number of row, and the number of column is equals to the length of time. Okay, this is important because in MATLAB, if you want to plot a graph, the x and y needs to have the same size, and that's why we are using the length of t, so that the SIR and t has the same size. So the same things goes to I and R. Okay. The next thing that we are going to do is to initialize our value. Okay, so we are going to initialize the total number of populations. Now, the total number of populations is actually S plus I plus R. So in this case, we are declaring the total number of population is 100. Therefore, S plus I plus R is equals to 100. And then we are going to declare the number of infected. So we are going to declare the number of infected 1, and the number of removed is of course 0, because there are no individuals is removed when we first start our simulation. Okay, so the number of susceptibles is n minus I, because like I said before, the total population is equals to S plus I plus R. Therefore, S equals to n plus I plus R. And we know that R is equals to 0, therefore S equals to n plus I only. Next thing that we are going to do is declaring the probabilities. Okay. So from the Markov chain that I had explained, we have two probabilities, which is the P infected, P inf. Okay, P infected. P infected is the probabilities for susceptibles to be infected. And we have P remove. Okay, P remove is the probabilities of the infected to be removed. The probabilities is for each individuals. Okay, that is one thing that you need to remember, that our probabilities is for each individuals. We are going to create a for loop for I equals to 1 until 99. Okay, why is it 1 until 99? Because this is based off our x-axis or our time vector. Okay, as you can see, time vector is 1 until 100. Okay, so I guess you understand why is it why we are using 99 instead of 1 until 100. But if you don't understand, let's just move on and I will explain to you later. Okay, so the next thing that we are going to do, we are declaring the total infected equals to 0, total remove equals to 0. This total infected and total remove is actually the change of the infected and the change of the remove. You will understand as we move on. Okay, so the next thing we are going to do is we are going to determine whether each susceptibles will be infected in that particular day or not. Okay, so we will start with if Si is not equals to 0, that means the current susceptibles is not equals to 0. If Si is not equals to 0, which means if the current number of susceptibles is not equals to 0, then we will do what's inside here. It is important that that we declare this, because in this part we are going to check whether each susceptible individuals will be infected on that particular day or not. So if there are no more susceptibles, that means there's no ones to be infected, right? Okay, so that's why it is important for us to make sure that then this part will be executed. So again, for loop j equals to 1 until Si. So why we are doing it like this? Why is it 1 until Si? Because like I said before, our probabilities is for each individuals. So we need to repeat the process for each individuals. The next thing is INF equals to bino RND 1 PINF. What this function will do, the binomial random, it will return either 1 or 0. And the probability for this function to return 1 is PINF. Okay, so this is where the stochastic happens. This is where the randomness happen. So let's say that the current susceptible individual is infected, therefore it will return 1, and we will update the TINF, the total infected equals to the previous total infected plus infected, which is 1 if the current individual is infected. Okay, and it will repeat for every individual, because like I said before, the probability that we are using, the PINF and the PREM, is for each individuals, so it will repeat for every individual. Okay, so the next thing is we are going to check for every infected whether it will be removed or it will stays infected. Okay, so it's just the same thing. As you can see, we have the first thing that we will do is we check whether is there infected or not. If there are no infected, then there is no one to be removed, right? Okay, so the same thing, we use the binomial random, and and that's all, I guess. Okay, so after we've done all of that, after we've update the latest status of every susceptibles and individuals, then we will update our data. Here we will write the next susceptibles, which is the Si plus 1 is equals to I plus 1 minus total infected. Total infected is the number of the susceptibles that has been infected on the current time or current day. Okay, so it will be minus. Next we will update the infected. Okay, so the next infected is equals to the current infected plus T infected. T infected comes from the susceptibles minus the T remove. Okay, and lastly, remove the next remove Ri plus 1 equals to previous R plus T remove. After we updated all our data, and this will be repeated for 99 times. Okay, so now I am going to explain why we do this until 99 only. Okay, because as you can see here, 99 plus 1 is 100. Okay, and as we all know, our SIR is only until 100. So what if we repeat this until 100? So 100 plus 1 will be 101, and that will return an error because our SI and R is only until 100. Okay, so after we've done all that, we will plot our graph. Let's see, let's run this. So let's run this. Okay, so this is the stochastic SIR model. The blue one is the susceptible, the red one is the infected, the green one is the remove. Okay, now how can you tell that that our SIR model is stochastic? Okay, so using the same value, the same probabilities, if you rerun it, you will actually get a somewhat different graph. Okay, I hope you see. Let me see. Okay, so here, can you see? Can you see how different is these two graph? Okay, so this is the stochastic SIR model. So usually when you hear people say let's flatten the curve, it's the infected curve that we are going to flatten. Okay, so that's why the red curve looks familiar. We've seen it on the TV. We've seen it on the internet. So let's just rerun it one more time to prove to you that our model is stochastic. Okay. Let's see. Okay. So we run it 3 times, and as you can see, we get a somewhat different graph using the same value, but we'll still get the different graph. Okay, I guess that's all from me. Thank you for watching this video.